Hello, AP Chemistry. This time let's take a look at how do we find empirical and molecular formulas, what's the difference between the two, and how is combustion analysis used to find empirical formulas. There's three basic objectives to this lesson: calculating empirical and molecular formulas, and then explaining how combustion analysis is used to determine empirical formulas. An empirical formula provides the relative number of atoms in a formula. It is the most reduced formula. So this is not necessarily the real formula. I'll give you some examples in a minute. The molecular formula is the real formula. It indicates how many atoms are actually in a molecule. Here's an example. Hydrogen peroxide, H2O2. That's the molecular real formula. Notice it's H2O2. You can take a 2 out of both. So when you reduce it, you simply get HO. That's an empirical formula. So if you're given a question that says, which of the following is the empirical formula for this molecular formula? All you have to do is reduce the subscripts. So make sure you have all the same elements and it reduces. Combustion analysis is just an experimental method to find empirical formulas, and we'll go over that in a little bit. How do you calculate an empirical formula? There's three basic steps. Number 1, mass to moles. Number 2, mole ratio. And then number 3, those are your subscripts. There might be one little extra step in there, but that's basically it. So the first thing you want to do is convert the mass to the moles. Now, a lot of times a problem won't give you mass, it'll give you percents. Well, if the percents add up to 100%, you can assume you have a 100-gram sample. Then let the percents be grams. So if it says it's 65% oxygen, you have 65 grams of oxygen. Now you all know how to go mass to moles. So take all those masses, turn them into moles. So you're dividing by the element. So grams of oxygen means you're dividing by 15.99 grams of O, not O2. So be careful there. Find the mole ratio. And all you do here is you look at the moles that you just calculated, pick the one that's the smallest, and divide everything by that smaller number. And if you get a number that's pretty close, like 1.98, you round it to 2. But if it's 1.49, 1.51, you leave it at 1.5. So those answers you just got, well, those are your subscripts. But you would never use 1.5 as a subscript. So what you do is you multiply by the smallest number that it takes to get to a whole number. Well, 1.5 times 2 is 3. Sometimes you multiply by 3. Very seldom do you have to multiply by a bigger number than that. And I'm going to point this out again in a little bit, but one of the key points when you're doing this math is when you go grams to moles, make sure you go to about 4 decimal places. Ignore sig figs. Trust me, if you round too early, too soon, you tend to get really crazy answers. Let's go ahead and take a look at an example of how to find an empirical formula. So the problem says, calculate the empirical formula of a compound containing 52.14% carbon, 13.12% H, and 34.73% O. They're percentages. So remember, if you have 100%, you can assume you have 100 grams, and then you can just make the percents be grams. So really you have 52.14 grams of carbon. Turn that into moles of carbon. Now notice again, I wrote 4.3413. I went to at least 4 decimal places. Trust me on this. Do not round it too quickly. I did the same thing for H and O. So you'll notice in the middle there, my moles, 4.3413 moles of carbon, 13.0159 moles of H, and 2.1708 moles of O. So we've done the first step. We've done mass to moles. Step number 2, mole ratio. So you pick the smallest mole, in this case 2.1708, and you divide everything by that number. And I rounded, you get 2, 6, and 1. please do the math yourself, and you'll see that you really don't get 2, you get something like 1.9998. That's okay, you can round that to 2. And 6 was really more like 5.9999. So go ahead and do the math and double check that on your own. So number 1, mass to moles. Number 2, mole ratio. Number 3, those are your subscripts. So C2, H6, O. Now what if, for some reason, that carbon would have turned out to be 1.5? Well, I can't write C 1.5, so I would have multiplied all of the subscripts by 2, and I would have gotten instead 3, 12, and 2, just to let you know how that works. How do we get the molecular formula? To be honest, you do the hard work finding the empirical formula, and then to go to the molecular formula, it's actually pretty easy. Take the formula you just obtained and find the molecular weight of it. Then you compare that to the real molecular weight, and that's going to be given to you. There's no way you could do these problems if they didn't give you that information. So take the bigger number, which is the real weight, divide it by your number, which is probably smaller, and you'll know what you need to do to the subscripts. So let's say, for example, the real weight is 34, your formula is only 17. Well, 34 divided by 17 is 2. That means you need twice as much stuff. So all you have to do is multiply all of your subscripts by 2. And this is actually the case with hydrogen peroxide. The empirical formula is HO, and the weight's about 17. The information given is going to tell you that the real formula is 34. Well, 34 divided by 17 is 2. So you take the 1s, which are the subscripts for H and O, multiply by 2, and you get H2O2. It's really that easy. Normally, this is where we would do a POGL on combustion analysis, but I think just touching on it here will be enough. The point of this is, how can you do an experiment, collect the data, and turn that into an empirical formula? Well, if you look at this picture, and this is from a POGL, what you have is a sample. It's heated, water gets absorbed, carbon dioxide gets absorbed, and then the rest of the oxygen is just run off. And what you look at is this. You get the mass of the CO2 produced, and you get the mass of the water produced. So how did they get the empirical formula? So where's the magic? Well, here it is. If you take the mass of the CO2, you can turn that into moles of CO2. You all know how to do that. That's pretty basic. Well, how did I get moles of carbon? Can't you take moles of CO2 and turn it into moles of carbon? If you look at the formula for CO2, every CO2 has 1 carbon. So if you have 1 mole of CO2, don't you have 1 mole of carbon? So the moles of CO2 and the moles of carbon are the same. And then you do the same thing for water. Moles of water, mass of water to the moles of water. This is a little trickier though. For every mole of water, there are 2 moles of hydrogen. So notice I doubled the values to get moles of hydrogen. Now what you do not see in this data table at all is what we did in the POGL in one of the questions. Well, where did they get CH4? Where did they get CH3? Well, you might not have realized it, but they actually have already done the first step in finding an empirical formula. Mass to moles. Well, what's the second step? Mole ratio. So if you look at the moles, you have moles of carbon, 0.6232, moles of hydrogen, 2.496. Take the bigger number, divide it by the smaller number, and you get 4. So 1 carbon and 4 hydrogens. And when you do 1.997 divided by 0.6650, you get 3. 3 hydrogens to 1 carbon. So it's basically what we were just talking about, it's just with actual experimental data. Holy cow, what in the world is this? Well, you can do combustion analysis with things that have carbon, hydrogen, and oxygen. So in this case, they have the moles of carbon atoms, they have the moles of hydrogen atoms found the exact same way we did before. And then they do a little bit of math. There's a little bit of subtracting involved and whatnot, but ultimately you can get moles of atoms, of oxygen atoms. And again, they didn't show you the second step, mole ratios. So if you look at sample number 1, the smallest mole is the oxygen. So you would divide everything by 0.2181 and you would get C2H6O. I just simply wanted to show you that you can do combustion analysis for different compounds that have carbon, hydrogen, as well as oxygen. It just takes a little bit more math. I don't have anything on this slide. I just wanted to do a quick review. So remember, an empirical formula is just the most reduced formula. So if I simply gave you CH2O, that could be a number of different things. C6H12O6, glucose, it reduces to CH2O. So an empirical formula is just a reduced formula. It's not necessarily the real molecular formula. The molecular formula is the real formula. So the hard part is finding the empirical formula. So remember, there are 3 steps: grams to moles, mole ratio, and then that number is usually your subscript. Now remember, if you get some crazy thing like 1.5 or 2.5, you need to multiply by the smallest number you can, usually 2 or 3, and you'll get your overall subscripts. And combustion analysis is just an experimental way to collect data. Usually you collect the mass of CO2 and water. When a hydrocarbon is burned in oxygen, it's a combustion reaction. And then you can turn the grams of CO2 and the grams of water into moles of carbon dioxide and moles of water, and then into moles of carbon and moles of hydrogen, and do a mole ratio. Bam, you have an empirical formula. I hope this helps you guys do your homework.